In the selection combining, as we said earlier, we will choose the best SNR or the highest SNR given our, let's say, n antennas. Okay, so the branch or the antenna with the highest SNR is chosen, and the other branches, they are disregarded, so we don't use the data coming out of those branches. Okay, so in this case it's very simple. So it's a multiplexer, right? And we know we don't need to estimate the phase and to do some signal processing, as we'll see in the MRC and in the equal gain combining. Okay, um, but we need to monitor each SNR on each branch, I mean. Okay, so mathematically the resulting SNR is the maximum of all the m or n branches. So okay, now we get this is the maximum SNR, right? So we need to find the outage probability, or the CDF. Before that, we need to find the CDF, the cumulative distribution probability of the SNR, right? So actually it is the maximum of uh, the received SNRs. In the case of the CDF, we will need to find the probability of being less than some value gamma. So this is called order statistics. Order statistics. We need to find the maximum value or the minimum value of some uh, group or set of random variables, right? So simply, actually it is the product of each CDF. So the order statistics of m CDF, when we are taking the maximum value, is actually the product, which is quite simple. Now recall that the PDF for each SNR is an exponential one, right? So here the product, it will be the PDF times or to the power m, since given that we have n branches here, right? N branches. Okay, so this is very simple. So since all of the branches have the same average SNR, which is gamma bar, and gamma node actually is the cutoff SNR or the zero sensitivity, just we can use equation 7 to find the outage probability. So it's very simple here. The average SNR, on the other hand, is also simple. We find the harmonic value of the m branches, which is actually you sum 1 over 1 plus 1 over 2 until you reach 1 over m. This is called the harmonic value, right? And you multiply it with the average SNR. So as you can see that the average SNR increases, but not by a big value actually. Let's take an example on section combining. Okay, we need to find the outage probability for a system using binary phase shift keying modulation at a bit error rate of 10 to the minus 3. Of course, we are assuming a Rayleigh fading, and we are using selection combining diversity with 3 branches. Okay, and assume that all the branches are identical with an average SNR of 15 dB, right? So we need to find the outage probability. So the first thing we need to do is we need to find the required SNR here. So this can be found out from the bit error rate. If you recall, the bit error rate of the binary phase shift keying is the Q function of the square root of the double of the SNR. So EB over node is the actually is the SNR, average SNR, as you see in some cases. Okay, so we can find them using the inverse Q function, and we get the SNR to be 4.81. This is the linear SNR, right? This is linear. So we need to have an SNR of 4.81 to achieve a bit rate of 10 to the minus 3, right? So this is the um, gamma node here, right? Great. Now gamma bar is given in log scale, so we need to convert it back to linear scale here, right? Now we want to find the outage probability when using one branch, which is actually we're not doing anything, two branches and three branches, using selection combining here, right? So just you simply plug in the values here, and as you can see, when you increase the number of branches, the outage probability is reduced.